Hey, so another really nice day out to go and record, and it was 40s last night, but now it's in the 50s, and honestly, like I feel like it's a lot warmer today than it was 2 days ago on Tuesday, when the neighbors had their lawnmowers going. Anyway, yeah, so this is probably going to be the last lecture I record for my tomography class during the actual semester. I plan on putting up a couple more, just on request of students. This extra format means I have extra time to do other weird things like that. The face of education really has changed, like where, you don't have to be in a classroom anymore to officially be in a class. Which is interesting. I mean, before there were obviously like online classes and even online colleges, but I mean, like it didn't happen on such a massive scale. Anyway, yeah. So I mean, I've sort of fallen in with a lot of these like YouTubers that I see doing all sorts of educational videos. I think it's really fascinating. Sometimes I have trouble stopping watching and getting back to work. There's this guy, I think his name is Simon Roper, who does like a historical linguistics. He's an amateur historical linguist, but his videos are all really interesting and really fun. Maybe I'll put a link. You can go check them out. Anyway, yeah. So back to what I'm here to talk about. So today we're going to talk about motion tomography. Motion tomography is sort of this idea you can use low-cost gliders to extract information about fluid flows. And so the idea is they have these gliders, which are really just really simple submarines that can keep a bearing and push on at like a constant rate. And so then if you put them in completely still water, you drop them in, and then they travel along, and you don't hear from them until they surface later after a fixed amount of time. And when they surface, you get their position. Now, if it was still water, you know exactly where they should end up, and they should be on a straight line, and times the amount of time they were going that way, because they can maintain a constant speed and a constant direction. But in the face of fluid flows, you'll have perturbations to what's going on. So if you have some really light flows going on in your in say the ocean or something like that, then it'll be moved just a little bit, and if it's a lot, then it'll be somewhere completely different than you expect. And overall, what you can see is that the difference between where you expected it to end up and where it actually did end up can be represented as an integral. And this ends up being sort of a tomographic integral, where we have, it ends up being a tomographic sample. Where we have now we have the integration along our flow field, as a difference between where you ended up and where you started. And so but again, it's not going to be a straight line, it's going to be a curvy line, and that's where we end up using these occupation kernels to sort of replace this the radon transform in this new setting. Now when I say new setting, I mean it's been going on. It's been studied for probably the past 5 years or so. I think it was like a 2015-2016 paper out of Fumin Zhang's group at Georgia Tech, and he had a graduate student, Dong-Sik Cheng, and I can list. I'll just put the citation up here for all the other authors. And their approach to this problem was to basically set up a now I'm paranoid, my microphone's not on. No, it is, okay. Their approach to the problem was to discretize their region, just like what we did with algebraic reconstruction techniques, and they basically had a whole bunch of 0-1 functions all across it, and they also did it with some kernel functions like Gaussian RBFs and stuff like that in another algebraic framework, and then they used the Kazmark method, which we've already said it actually doesn't perform nearly as well as, say, continuous methods like this, filter back projection, but it gave them sort of an initial, way of, resolving this problem. Just like we had out of CT scanners, the Kazmark method was, Kazmar's method was, sort of the first attempt at image reconstruction there. And so, then I was working on some problems in system identification with Rishikesh Kamalapurkar and Benjamin Russo, and then they brought up this problem that was really similar to the sort of things we were doing, and so then I concocted an algorithm that would which I'll present to you today, that actually ends up working out fairly well as far as the flow field reconstruction. But this uses our occupation kernels. And so what's interesting is basically you can use your guess at what the trajectory should be, and throw that into an occupation kernel, and then you can use that to get a first order approximation of the fluid flow, and then feed that back into your dynamical system, run the dynamics again with your new guess, and then that gives you new trajectories to put into new occupation kernels, etc. So you end up having this sort of iterative refinement of your occupation kernels and their trajectories both at the same time. And so then later on, Ben put together some sort of conditions that you need in order to get convergence, and so then he ended up being the first author on that paper, because I mean that is a big contribution, and so then and then later on we connected with Dong-Sik Chang to see if he can help us out with actually running comparisons with his own method, and also consulting on the data and other things like that. And so we put together this really nice team between me, Rushi, Ben, and Dong-Sik Chang, and Rushi, I should also acknowledge, helped me develop the algorithm in the initial stages, and so then we all put in a lot of effort, and now we have 2 papers that are under review, one at the ACC, and that's where we just have the algorithm and just introducing it, and then we have another one under review at a journal where we are putting together where we put the algorithm and the proofs for that. It's more of a mathy journal, so they would care about this sort of thing. So what I'm going to do is I'm going to show you what this algorithm is, and then we'll go over some implementation details about it, and it should be fun. All right, so I'd like to thank all of my collaborators, for helping me out with this project. I really couldn't have done it without each and every one of them. I've been really lucky to have developed a really strong collaborative frame, support structure, and I couldn't be happier with the people I work with. All right, so I'm going to go ahead and cut off here, and we'll get into the lecture itself. All right. Okay, so let's go ahead and get started. So here we're talking about the problem of motion tomography. And so generally speaking, you have some sort of flow field. Now mathematically we're represented by a vector field of some kind, where you have a whole bunch of arrows going off in different directions, and you basically want to figure out what these arrows are. So we're going to break down the approximation. When we actually do the approximation, we're going to break it down to 2 different dimensions, and a lot of this is off the cuff, so we'll see how well I actually do in presenting it. Also outside with all the noises that come out here, and so so we'll see how all this works out. The general idea of the problem setup is that we end up having gliders. So we have basically low-cost gliders. There's no, these are submersibles. I don't know if I spelled that right. So they go underwater, and there's no contact while underwater. So these things could go for miles and miles and miles, and if you lose them, you don't want them to be too expensive that that you're suddenly like put out of your research funds. And so these are really cheap gliders that you just drop in the water and you say go. So there's no contact, but they can keep a bearing. That means that they have a compass, and they can more or less stay in the right direction. and then they can maintain a constant motor output. I'm not an engineer, but this is more or less how these things were explained to me. So basically, if it was in just regular, still water, regular still water, is there such a thing? If it was in still water in like a pool, and you let it go, it'll stay the same constant rate the whole time. So then between these two things, essentially if r is the trajectory that corresponds to this low cost glider, then basically what you have some speed times some angle, so cosine sine of theta, right? And so this is a unit vector, and some speed is going to be greater than or equal to 0, but it's fixed. I'd say greater than 0. We don't want it to stay still in still water. And so then anything else that happens to this has to be coming from the flow field, so f of r, wherever r is. And so notice this is independent of r. I mean, we don't care what the current position is. We're always going to be going the same speed. We're always going to be going the same direction. But what does depend on r is this position inside the flow field. And so basically, we're going to start here, and we expect that it'll come here if we just had a zero flow field. So this is sort of our expectation here. I think it's too high for what I usually chop. So that's our expectation. And then the reality is going to be something like over here. And so that was our expectation, but maybe the flow field actually diverged and went over this way and pushed the thing over this way. And so, although with these arrows, it should probably be more like up here, but whatever. And so then you have this discrepancy between your expectation point and where you were here. And so, then you can, talk about your initial guess. Let's put it in green. So your initial guess was, say, r naught dot is equal to s times cosine of theta sine of theta, right? Plus, say 0 for these dynamics. And so if you take a look at, say, r of the final time, you had some sort of fixed time at which it would arise. It's going to be r to t minus r naught of t, and this is equal to the integral from 0 to t of just the difference between the dynamics. So you had s of cosine of theta sine of theta from the first one, plus the flow field and what actually happened, minus s of cosine of theta sine of theta over here, and this is all say dt. Should dt there. Well, if you take a look at this, we end up having a cancellation quite clearly. This guy cancels out this guy, and all you're left is with this. And so this, if you take a look, ends up being the integral from 0 to t of f of r of t dt. All right, and so that is the difference between what you expected initially and what actually happened. But we have a problem. So if I'm trying to figure out a nice way to represent this, this guy is going to be equal to f if f was inside a reproduced kernel Hilbert space. And if we want, let's just keep it down to one dimension. So we'll say this is I, and so it's going to be, the ith component out of this, and we'll just call this fi here, and this will be the ith component out of here, where I is equal to 1 or 2. And so, then what you have is you have f inner product with, say, fi inner product with gamma of r of t here in H, if fi came from our inner product space. Now I'm changing everything to be scalar valued. You could do this whole setup with a vector valued reproduced kernel Hilbert space, but it'll be more or less the same sort of results if you use a diagonal vector valued kernel. But we haven't even talked about that in my class yet, so I'm not going to go too much in detail on this. We can just do this component by component, and it works just fine. So So basically, here we go. So this difference here actually represents our integral along the trajectory of our flow field, and so it represents this guy. Unfortunately, though, since we only have the the endpoint data here and here, or rather here and here, we don't actually know anything that happened on the inside. So this is an unknown trajectory, which means we can't make the occupation kernel that corresponds to that trajectory because we don't know what it is. So we have to do our next best thing, and the next best thing is going to be assigning it this. And so as a sort of heuristic, for now, we're gonna just put in r naught of t of h. So it's not the best, and this could be very, very far off if we had a very dramatically strong flow field, or I don't know, a moderately strong flow field maybe. So our initial guess has to line up at least close enough to r of t that the difference between these two guys isn't going to be too great. And so ways you can guarantee that is if your flow field is small, then if is small in magnitude, then you can go ahead and all right, there's an ant on the microphone. Hold on, we gotta blow on it. Sorry, guys. All right, I'll try to filter those guys out. Anyway, so basically, in order to make sure that these two samples are close enough to each other for computational reasons, you need that. And so making this assumption actually can feed into later an actual convergence proof. Let's review real quick what an occupation kernel is. And so if you didn't see the last lecture, for some weird reason, if you're in my class, basically an occupation kernel does this. So occupation kernel review. So basically, for a reproducing kernel Hilbert space, of continuous functions, it could just be bounded functions, to be honest, but I don't always find it necessary to make things quite as general as possible, but maybe that's why people call me an applied mathematician nowadays. So it's a reproducing kernel Hilbert space of continuous functions over, say, Rn, such that, actually we'll just start with that, and we'll call this Hilbert space H, and a continuous trajectory say gamma going from say 0 to t to r n, the occupation kernel in H corresponding to gamma is given as the function that represents the functional g mapping to integral from 0 to t of g of gamma of t dt. Now again, we talked about last time, you don't actually need gamma to be a continuous trajectory. It could be measurable and and bounded, and that would be sufficient for making this statement. And yeah, so it represents this functional, and so basically as g gamma is equal to integral from 0 to t of g of gamma of t dt, and it can be expressed. I can't write. Expressed as so if you want to actually evaluate it, is gamma sub gamma of x is equal to the integral from 0 to t of k of x comma gamma of t dt. So pretty straightforward. And this is a reproduced kernel Hilbert space, a real valued reproduced kernel Hilbert space. I think actually that this exact formula works out for the complex case. You just have to keep track of your conjugates, but otherwise it's fine. But okay, yeah. So that's what we have. And so basically what we're doing is we're saying, you know, we're looking at this f, which should have been fi. And basically what we're going to do is we're thinking of this as this functional that corresponds to r of t inside of our reproduced kernel Hilbert space. And so in that case, we can write it as this, and then we also have, and then we use this approximation with our initial guess. And so, so let's talk about the algorithm here. So what is the motion tomography algorithm? All right, and so let's go ahead and describe it. So like I said, you have some sort of flow field here. Try and make something that looks credible. I don't know, something like this. And those are arrows, by the way. This one is pointing out that way. Okay, and so yeah, so this is your flow field. And basically what you have is you have a whole bunch of gliders that you are putting in here. So you're going to start a glider here. So say glider 1, this is going to be glider 2, glider 3, glider 4. Assuming it's a constant flow field, you could also just use the same glider over and over again and keep dropping it in if you want to, if you only have one glider. You know, and so it's be say 5 and 6 and 7 and 8. And so basically what you're going to do is you're going to drop these guys in, and then you send them off on a certain bearing. You know, so you have some sort of angle, theta, and you know s. You send them out, and for a fixed time t, you make a guess where they're going to initially go. And so this will give you all of your initial values. So this would be say theta 2, this would be theta 1, this is s1 and s2, etc. And so yeah, so you just keep doing this, and you know, and you make your guesses. And so you know, given you know fixed thetas and fixed s's, you can generally speaking make a guess of where each of these trajectories are going to go. Okay, and so each of these is going to give us these sort of different R naughts. So out of each one of these guys, we're going to have all these, you know, true trajectories, of say R1, R2, R3, all the way down, and how many we put here? R8, if you want. Right, and so generally speaking, these are unknown. You know, we know endpoints. We know the endpoints, but we don't know the trajectory itself. And so, so the goal is going to be to figure out, you know, like if this ended up being, say, the true trajectory from, say, this guy, diverged and went off over here, then we know this point, and we know this point, and basically we know that there's a difference between these two guys. And so we're going to use that technique I mentioned earlier in order to try to get sort of a tomographic sample. Okay, so sorry, I had to take a break for a second there. Okay, so let's go ahead and talk about it. So yeah, this is a setting. So we have all these initial s's and initial thetas, and that, so we know that whole s. So basically we know, say, sj of times cosine of theta j sine of theta j, right? This is known. And so then what we have other than that is we have these unknowns, but we do know our initial guesses.
So we know the say r tilde of I'm trying to figure out the best way to say j comma naught. So this would be the initial trajectory, initial guess for trajectory j. Right, and so we know that because we can compute this computed with something like RK4 if you want. Technically, if you want to compute it with RK4, well, actually, this initial one is RK4 because it's just constant. I mean, you don't even need Runge-Kutta. You know it's a straight line. You can just use ordinary calculus. But in later on, we're going to have to use some sort of numerical method to compute iterative guesses at these trajectories. So yeah, so that's the basic idea. So we start with this initial guess, and then we're going to get an approximation of the flow field using these occupation kernels, and then we're going to feed that back in to our guesses and generate a new guess, and keep that going, and then that'll become the new guess that we compare against, and we do the whole routine over and over again.
Okay. So this is actually going to be the third attempt I tried at this algorithm. The first one was just sort of like a stumble through what I already put down in the paper. And then the next one, I was called in the middle of it, and apparently my iPad just dumped the entire recorded video. So I'm going to give it another shot. So here I'm going to, unlike just doing a straight algorithmic description, I'm just going to try to describe to you step by step what the motivation is, and how the reasoning that goes behind doing all this. And so yeah, hopefully this time it turns out well. It's the next day for me, and so it's I'm watching my children. They're at their nap time, and yeah, so hopefully they stay down long enough for me to get this recorded. Anyway, much more casual wear on days I'm not working. Not like I go anywhere. I mean, I'm always just home, but it puts you in the mindset of work, which is nice. Anyway, so yeah, so we're gonna go ahead and I'm gonna show you basically we start off with constant speed, constant direction, and assuming a zero flow field, and then that gives us a whole bunch of trajectories to build occupation kernels, which can then be used to try to interpret this difference between the endpoints of the true trajectory and our guess, and then we use those as tomographic samples, and then we do an inversion through just doing basically projection onto these occupation kernels. Then what's going to happen next is that we do another guess, and so we generate another trajectory, and when we generate this next trajectory, we're going to use that guess as our flow field for computations. This gives us yet another approximation of the trajectory, but still not the true trajectory, and so then those will give us occupation kernels to then again use with this this tomographic sample that we get through the difference of the endpoints, and then again we feed that back in. And so this is a combination of generating new trajectories using the new guess of the flow field, which comes through, say, Runge-Kutta, and then after that you compare the new endpoints. Mind you, you only have to do the actual experiment once, and all these new endpoints come from just the new simulation. And so then with a new simulation, you take the difference between two endpoints, gives you another tomographic sample, and then you use that tomographic sample and you do an inversion process to project onto the occupation kernels corresponding to the new generated trajectories. Now keep in mind, what would give you the exact result is if you compared it against the occupation kernels corresponding to the true trajectories for each one of the gliders that you send through. But unfortunately, that information is never really available. So the only trajectory you have is your estimation through your simulations for that trajectory, and hopefully as you keep iterating this process, those estimations of the trajectory will get closer to the actual trajectory. And so with a couple of assumptions, we can make some sort of guarantee like that, and so that's and I'll briefly talk about that at the very end, although it's getting to be a long video. Anyway, so we can go ahead and just jump into it, and I'll just write down everything I just told you. All right, so I'll see you in a few minutes, or well, see you in a few seconds. I don't know, It takes me a few minutes to get set up. It doesn't matter. All right, see you in a bit.
Okay, so why don't we go ahead and get started here then. So we're talking about the algorithm for motion tomography. And so I've already kind of previewed a little bit of it. The first thing you do is you assume a zero flow field. So we're going to assume our approximation f of 0 hat is equal to 0. And we're going to write and then we're going to generate some approximate trajectories. So generate trajectories. And so here we're going to be given a S1, S2, all the way up to S capital M, and theta 1, theta 2, all the way up to theta capital M. And so these are all basically our directions and our speed, constant speed. And also we're given, say, for the true trajectories, we have R of naught, all the way up to Rm naught, and then we also have R1 of t and R1 of t. So you know exactly where the trajectory started, and you know exactly where the trajectory ended for the true trajectory, but you don't know anything else. So what we're going to do is we're going to go ahead and generate the new trajectories. So we have Sj naught. So this is our first guess. I'll put a little twiddle here. And when we go ahead and we compute that, this is going to be Sj times cosine of theta j sine of theta j plus f naught hat of rj naught total. Of course, this is identically 0, but we'll need this form later. And this is an initial value problem where we say r tilde j naught at 0. Well, we're going to make that match rj at 0. So the true trajectory that corresponded to that. Okay, so then we generate trajectories. This should be dot, and so it's a time derivative, and so it's a differential equation, and so we use, say, Runge 4 or something. Whatever your favorite initial value problem solver is. Okay, so what you get then is you have, in this case, it's just going to be a straight line, right? So because this flow field was 0 and this is constant, so we have the derivative is equal to a constant. It's a straight line, right? So you get like all of these different trajectories. Say r 1 0 tilde at 0, and this is r1 comma 0 tilde at t, etc. And so then what you can do then is you can take a look at this. And so we ask what is, we assign, say, dj comma 0, this quantity, which is rj at t minus r tilde j of 0 at t. And in this case, we're going to get integral from 0 to t. This guy was also being directed by this constant piece, and so when you take the difference between the true trajectory and the approximate trajectory, these terms are going to cancel out underneath the integral, and so all that's going to be left is the true the true field, which was given like this, minus your approximation of the field, rj 0 tilde, right? And so that gives you, and then this is dt. You put t here, and so that's exactly what you get here. But in reality, we know for this first attempt, this was just 0. So dj naught then is equal to the integral from 0 to t of f, which is our true slope field, And here we're just thinking of this, yeah. I should really honestly put I here for each component. Well, no, actually it's a stack of them, right? So that's fine. So we have Rj of t here, dt, and we know that this is the integral of f. We know it's f against the occupation kernel corresponding to Rj t, or we'll just say Rj dot, right? And this is inside of our reproduced kernel Hilbert space. Now, we don't actually have this information. What we actually have, so if we want to go ahead and get like a perfect approximation in terms of, or the best approximation we can with these occupation kernels, what we're going to do is we would ordinarily take gamma of R1 against gamma of R1, so we're the Gram matrix here. So gamma of R1 against gamma of Rm, and Rm gamma of R1. So occupation kernels correspond to each of these guys. Rm occupation kernel correspond to Rm, etc. Right. So this is what we would do, and we'd find some weights. So say W1 down to W m, and this would be equal to, in this case we have dj 0, or say we have d1 0 down to d1 dm 0, right? And we'd be done. That would be the best possible approximation we can get with these occupation kernels, just because f would be projected onto them, right? But the truth is we don't actually have any of the RJs, and so the only thing we actually have available to us are these twiddle guys. And so in this case it's a not value. And that's the best we can work with, because all we have are our estimates of what the trajectory should be. And so then, yeah, that makes things difficult. So then what you end up getting after all this is you get f1 hat, so our next approximation of x, is equal to, say, j going from 1 up to m of wj, comma, if you want, we'll just say 1 and 1, wj1, against the occupation kernels corresponding to rj not of, just rj not and this at x until. So this ends up being our next approximation. So this is our approximation of the flow field. Okay, so it's not nothing. I mean, we have something here. But now what we need to do is we need to, go ahead and do all this over again. So, so the next case is what we do is we generate trajectories. And so we're going to make R1 at J1 now, dot, is equal to Sj against cosine of theta j sine of theta j plus our flow field of 1 at rj1 tilde. Right, and so then we know again r tilde j1 at 0 should be equal to rj at 0, right? And so we go ahead and we do this, and and so instead of getting lines like what we had before, we get some sort of, maybe something that's a little bit closer to what worked. And so, so this is going to be, say, r, say 1 comma 0 at t tilde, and this is going to be r 1 comma 1 at t tilde. And we have possibly this guy over here might have been, say, r1 of t, and this is what we're trying to get. And so the idea is that this should be closer than the first guess. So then what do? Well, we generate this next bit say we say d of say j comma 1 now is going to be equal to r1 or rj at t minus rj1 tilde at t, and this is going to be the integral from 0 to 1 of little f of rj at t minus f hat 1 at rj1 t little t tilde dt. Right, this is what we got. And so if I want to get at this approximation, I need to add this over. And so then I see that dj1 plus, we can express this in terms of an occupation kernel that we actually know, since we know this, we know f because we made it up, and then we also know this occupation kernel because this corresponds exactly to our trajectory, r tilde of j1. And so yeah, so that's ends up being our tomographic sample here of f. So this is little f at the occupation kernel rj here at h. Okay, and so again though we still don't know this, and so while we're still trying to basically get an approximation, basically using the same exact formula here. So let's copy that. So then what we end up getting here now is this. Move that over and use some erasers. Get rid of all these zeros because now we have ones, and that's that. So just like before, we don't have access to the true trajectory, but we have our new approximation. So let's say 1 1 1 1, put 1 here, put 1 here, 1 here, 1 here, here, and here, and don't forget the commas. Oh, there's an extra comma. There you go. And so now we're going to get for our second approximation, and now we have d11 down to dm1, but now we also have to add in this extra bit of f not at gamma r tilde of 1 1 down to f not hat at gamma of r m1 tilde, and yeah, that's what we have. So then what we have after that is that we're going to end up having f hat of 2 at x is equal to the sum of wm comma 2 at occupation against these occupation kernels m1 at x. This is for, oops, sorry, not m, that's j, j equals 1 up to m goes here. And so there you go. So you keep going ahead and iterating it, and so you hope that these guys are refining and getting closer and closer to the exact answer, and then in a second I will show you exactly the sort of conditions that we need in order to get this sort of convergence going, or at least give you a high level overview of some of the other things you need. But generally, given a few assumptions, you can make this actually work, which is nice. Yeah, so that's the algorithmic description of this, and yeah, it works out fairly well numerically, and yeah, I guess here maybe we should just go ahead and go to the theorems, and so I think that's here. Okay, so here are a smattering of theorems that we actually needed for the proof of the convergence. And essentially, it's pretty standard to use this contraction mapping principle. It's the sort of when it's used if you do, say, solutions to initial value problems, etc. And so the idea is that we're trying to come up with some sort of iterative scheme where if we keep applying it, we end up getting convergence. And so basically, P here is our algorithm, and xk and xk plus 1 play the role of our function approximations. And so you basically, what you need to do is you need to show that you end up having a contraction. So after, so basically if you're, let's say, close enough to the point itself, then maybe the, the distance between pxk and pxk plus 1 is always going to be bounded by that distance is always proportional to the distance between xk and sk plus 1, with proportionality of being less than 1. And so that's more or less what we're trying to do here. And so if you take a look at say proposition 5 here, essentially what we're doing is we're taking a look at for two different approximations, fn and fn plus 1, say, and you take a look at the approximate trajectories you get using those as your foundation for your slope field. You end up getting this guy, and so you can see that this is the distance between these two trajectories is actually proportional to the size of the distance between the approximations and the Hilbert space norm. And that can be shown with Cauchy-Schwarz plus a little bit of calculus. And so then next thing you want to do is you want to show that the occupation kernels themselves sort of follow that. And if you take a look, basically if you have two different trajectories, gamma 1 and gamma 2, and then you have some sort of like continuous parameterization between the two, and this is called a homotopy, so you gradually morph from one to the other, then basically this mapping where you go over the index for that morphing, this mapping to the occupation kernels is continuous, and so that's sort of a first indication that this is a good thing, because if you satisfy something like this, then you're continuous, and so continuity, maybe we have some hope there. But unfortunately, when you get to this corollary, we already established this guy, but when you look at this side, this isn't quite strong enough for what we need. What we are really hoping for is that we'd end up having a power of 1 up here, and not just 1/2. And so, this is. So while this is a nice little result here out of corollary 7, ultimately in order to get convergence to work, we have to add an extra hypothesis, and we have no indication that it's false, that you can get rid of this and you have this sort of convergence. So we would say that these occupation kernels are sort of Lipschitz with respect to the two approximations. That's what we would say. Anyway, and so then when you add in that extra assumption, then the convergence actually ends up working out very cleanly, and then from a computational standpoint, this ends up giving us some sort of lower bound on the eigenvalues of the projection matrix, and this result ends up being really close to what you see for projection matrices for just regular kernels and scattered data approximation, and so that ends up being fairly encouraging. Anyway, but yeah, so just to give you an idea of the theorems I went into here, and so it's sort of a fixed point iteration scheme, and eventually I'll have a preprint up on my website if you want to take a closer look yourself. But yeah, so that's the algorithm, that's motion tomography, and when I get a chance, either I'll put it in this lecture or I'll make a whole new video just going over the all right, so I think I might have said that I'm not going to put MATLAB lecture in here, but it took me an extra day to put even the regular lecture together, so I had a few extra minutes that I can just go ahead and start up the code. What I'm going to show you here is just a simulated example. So we have a simulated flow field, which is sort of a sum and difference of a bunch of Gaussians. What's nice about it is that we actually have access then to the actual trajectories, which will allow us to do a comparison to see actually how close we get to the true solutions. We also have done work with the Glider-Palooza data, but there's no ground truth because that was actually all this work in a real world situation. And so here we're just going to use this simulated example just sort of give you an idea. You'll see in the code that I have a few sarcastic remarks to myself to get this thing shaped up a little bit more. There's a couple of loose ends I still wanted to go and tidy up, but it works well enough for what I'm going to show you. So if you take a look at over here, what's working out is that we are using the exponential dot product kernel. And so this is the kernel that I told you about that corresponds to what we call the Fock space. And so essentially, we're going to go through here, and so we have, so we're using this flow field 1, and let's see, just trying to see in here. There's been a couple of us working on the code. Yeah. Anyway, so here we're using this flow field. I'm saying use. So I'm saying to use our simulated flow field. I'm saying 10 iterations, but let's start with just 2. And our time variable is just 1, and our step size for all of our simulations is 0.01. And so so if I go ahead and push play. Oh, and our mu for our exponential dot product kernel, by the way, is 50, which might seem a little large, but unlike Gaussians, exponentials have just e to the x times y inside of them. So if x and y get to be very large, you're hosed. Anyway, it's exponential to a really large number that's going to be numerical infinity. And so so you need to divide by some other parameter to scale that down. And so usually you want to get to the scale of, something between like 3 or something like that. But, whatever ends up working. And so here I'm telling it to plot the true solution and let's see. True solutions, yes. All right, yeah. So plot the true trajectories, and here this third one says to use the approximate trajectory from that point. So if I go ahead and push play, it should only take a moment. There we go. So with 2 iterations, we're not doing too bad. Actually, looks like we're pretty close. And yeah. So with, let's see. Let me change things up just a little bit to make things break, because that's not exciting when you don't see it. Let's see. So let's go with our anticipated trajectory initially. Okay, so here, don't listen to what this says. It's not the paths with 2 iterations, but it's the anticipated one. So this here is the straight line paths that we had guessed. And just using the bearing and the constant speed. And so that told us that roughly we should expect it to end up in all these places. And so here, this one started here, and you can see it over here, and it looked like it got to about this point. And that makes sense because we're sending this off in this direction, and sending this off in this direction. But for this one, we guessed that our flow field was 0, right? So we should have expected to just keep going as it was. But here all the arrows point against it, right? So it stops a little early because it had to fight all those currents. And so yeah, so you can see all these other things going on. You can tell where they started and where they ended because the start points are identical between these two. And so this has moved up to about here, and just because all these arrows are pushing it up. But on the 0 flow field, we had assumed it was just going straight. So yeah, so then if I go ahead and yeah, this is kind of working a little too good. And so let's see. I don't know. You can see it doesn't actually even take that long to run this. So I can run this at like say 10 trajectories. And I press play. I think it takes about 6 seconds. That's what I have here at the bottom. You can see I already ran it before I started recording. Just make sure it runs. And so yeah. All right. So now this is giving us our approximations of their paths, and you can see that these match up almost identically to what we have for the true paths and the approximate paths. So, and the flow field you can see in the background. This is the approximate flow field here, and this is the true flow field, and you don't really see a difference between them. So that's really nice. And then just for to make yourself feel better, you can run this say 30 times, and that should take about 18 seconds. And just make sure that it did actually converge and not it's not going to suddenly start blowing up. Of course, you don't have any numerical guarantees here. We are making assumptions that guide our notion of convergence here. But yeah, just give it a second, and it should come up right about now. There we go. And so yeah. So what do we have? They look identical. So this is with 30 iterations, and doesn't seem to have changed at all. So that's good. It's the sort of leads us to trusting the sort of convergence here. No need to keep it at 30. Might as well put it back to 10. And yeah, let's see. Anything else we want to talk about? Let's see. So here you can see we're using an RK4 method to generate the approximate paths in our iterations, and yeah. Let's see. Yeah, we have a parity check because we're going to use Simpson's rule for all the so we use Simpson's rule for all of the sorry, just blanking here. For all of the occupation kernels and inner products, and so Simpson's rule generally requires you to have an odd number of points, and so we just trim one off if we need to. If h is small enough, here it's 0.01, it won't really make much of a difference. And yeah, so here we have our approximation, just initial approximation is 0, 0. And yeah, and so then other than that, we just go ahead and we start doing all this. So this is basically a whole bunch of stuff that allows us to get the gram matrix, and so it's a bunch of clever tricks to do with matrices. Essentially, we make a Simpson's rule matrix that we then do pointwise multiplication with a sort of our exponential dot product kernel. So here we have x, y. Basically we compute all of the inner products between two different points, and for two different paths, exponentiate it, and then after that we do pointwise multiplication of Simpson's rule, sum it twice, and then we get a double integral, which represents one of our components of the gram matrix. And so then we go and we do this in a double loop. Usually you try to avoid loops as much as possible in MATLAB, but you can't get around it in some cases. And then after that you'll have your gram matrix. And then up here, we have our compensation F that we're adding to that D that we talked about before. And yeah, and so then we do it once for the weights that we get for the X variable, and then we have the weights we have for the Y variable. So out of the algorithm description I gave you in the notes, I sort of left that part out. So basically, you're going to be doing this twice, one for the X variable, one for the Y variable, and then but once you do that, you're done. It's only two different times, and ultimately it comes down to the same gram matrix. It's just you use a different component out of the D variable. And yeah, so then the next F is these weights, and then times our occupation kernels, and we made a function to evaluate them. Okay, and so yeah, that's that. Yeah, and so the rest is just a plot command. Anyway, yeah, so not too bad. And so like I said before, takes about 7 seconds here. And then you can see it's nearly a perfect representation for the simulated flow field, and then for the one that wasn't, and then we compare it with Kazmar's type methods, it actually ends up approximating the simulated flow field better than the Kazmar type method, and then it does a comparable job in the real data. Of course, we don't know what the ground truth is for the real data, so we don't have a baseline comparison, but it does do a very similar job to what previous motion tomography work did, using works of like Dongxi Chang and Fumin Zhang. Apologize if I've botched those names, but yeah, so we're pretty proud of this, and yeah, this is our little contribution so far to tomography. Anyway, so I guess I'll go ahead and stop here, and we'll go back to yesterday when I recorded my outro. All right, thanks for watching, and I'll see you next time.
Okay, so yeah, that's motion tomography. So that's yeah, so I guess that really concludes everything I'm going to present to this course. This is sort of my own contribution to tomography, and honestly, it can be generalized in a lot of different ways. And so my team and I are working on new and different angles that we can take with tomography using occupation kernels. And this team, includes Rushikesh Kamala-Porkar, Benjamin Rousseau, and Dong-Sik Chang. And yeah, we're excited to see where else we can take this. Yeah, thank you for hanging in there through this course with me. And I'll put a couple extra lectures later on, but I don't know when I'll be able to get to them. But yeah, I hope to have you guys hang around and subscribe to my channel. And yeah, I'll keep posting new and exciting things. And I'll try to do some different content too, whenever I actually get the time. All right, so thanks for watching, and yeah, I'll see you next time.